MPC. So generally when we design MPC protocols, we assume that parties can communicate over both point-to-point and broadcast channels. But in practice, it makes a big difference whether you're assuming that they are communicating over point-to-point or over broadcast. So specifically because broadcast is an expensive resource, in practice, how do you realize it? You either assume a public bulletin board like a blockchain, or you actually implement it using a protocol over point-to-point channels. But no matter which way you decide to realize it, it is expensive. Specifically, if you decide to implement it using a protocol over point-to-point channel, then it has been known since the 80s that any such protocol for deterministic broadcast would need at least T+1 rounds, where T is the number of corrupt parties. And even if you use these randomized broadcast protocols that have constant expected round complexity, those constants are still high. So typically when we talk about optimal round complexity and so on, sometimes we are not super mindful about broadcast. So if we want to truly analyze the exact round complexity over point-to-point channel, we might want to be careful about this. Because it may turn out that you take something not round optimal, like 7 rounds, that is using broadcast in only 1 round, and maybe that is taking you fewer point-to-point rounds compared to, say, something that is round optimal with 4 rounds, but using 2 rounds of broadcast. So when you're trying to analyze exact round complexity over point-to-point channel, you should sort of demarcate which of them are using broadcast and which of them are not. So this has been something that it has been in the attention of the community since a while. And especially in the context of verifiable secret sharing, thanks to these early works, there has been more of a demarcation about the round complexity in this sense, that the rounds that use broadcast versus the rounds that do not. And however, in the context of round optimal MPC, this was brought into attention more recently by actually Ran Cohen, Juan Guerre, and Vasilis Zikas, who are all in the room. So they actually brought it in attention in the context of this setting of dishonest majority with setup. So for this, 2 rounds are known to be optimal. And what they did in their work is that they analyzed all possible broadcast patterns in this 2 round. So they assumed that in the 2 rounds, say, none of them used broadcast, or only the first one used broadcasts, or only the second one, or both of them. So they looked at all possible patterns, and for each of them, they basically analyzed what is the best kind of security guarantee that you can get. So they did it for this setting, and then this was basically continued by a line of works by my collaborators from Aarhus and Edinburgh, and we were looking at the same question, but in the context of round optimal protocols in the plain model, as well as in the honest majority setting. So now I want to clarify that each of these basically are involving a lot of broadcast patterns. Because, for example, if you think of a 4-round protocol, now for each of the rounds, you're going to consider all the combinations that it uses broadcast or not. So you'll end up with like 16 combinations just for the 4-round protocol. And then for each of them, we are trying to understand what is the best guarantee you can get. But I did not want to overwhelm you with like big tables of 16 combinations and so on. So then I thought I will just sort of summarize some of the recurring or common patterns that came up in these line of work so that you can have some of the main takeaways. So one of the main takeaway is that in almost all these settings, it turned out that if you do not have broadcast in any of the rounds and you have only point-to-point channel, then it turns out that that is still sufficient for this weakest notion of selective abort, where the corrupt party is obtaining the output, and it can also select which of the honest parties is obtaining the output. So if you're happy with this notion of security, then you can get the same round complexity as the round optimal protocol, and you can just avoid broadcast altogether. However, if you want something stronger, that you want the honest parties to be in agreement about the output, and you want unanimous abort, so for this, it turns out, again, almost in all the settings, that the first earlier rounds can be over the point-to-point channel, and if you just have the last round over broadcast, then that is sufficient for you to get unanimous abort. Now, these are the upper bounds. So this was shown by means of constructions having the round complexity same as the round optimal protocols, and then we showed that this is sufficient. Now, if we move to even stronger guarantees, like say that you want identifiable abort, that you also want to identify the cheater, now is where broadcast starts becoming more and more relevant. So here, it turned out that for both the settings of with setup and without setup, but just for the dishonest majority case, it turned out that you need to use broadcast in each of those rounds. You can't replace any of those broadcast rounds in the round optimal protocols with point-to-point channel. So basically, the existing identifiable abort protocols that we have, they were round optimal, but they were also optimal in terms of the broadcast that they are using. Okay? So this was a lower bound result. And then, but in the case of honest majority, the situation is more optimistic in the sense that you can get rid of some of the broadcasts. Specifically, it turns out that in the last round, you can always sort of remove the broadcast and have it over the point-to-point channel instead. So again, this is a very sort of a selected view of the results. And I focused mostly on the extreme cases and what is happening in the last round. But in the rest of the talk, I want to sort of give you a little bit of a flavor of some of the upper and lower bound techniques, which probably have other applications. So I'm going to be just giving you an upper bound technique for the honest majority case with setup, and one of the lower bound techniques for the, again, honest majority, but in the plain model. But these might involve some other broadcast patterns also, but I'll explain to you as I go. OK, so before I tell you more about the upper bound, so what is the main challenge that happens if you suddenly remove broadcast? So for simplicity, assume that you had a 2-round protocol where the first round was using broadcast, and this sender was broadcasting this bit 0. Now suppose you try to remove the broadcast from this round, then what happens? You're basically opening yourself to the possibility that this sender could now be sending inconsistent bits to different honest parties, and maybe to some of the honest parties, it's even dropping the message. And now the problem would be that in the second round, if the honest parties start reacting based on the version that they got, this will be a problem. Because if honest parties start responding to inconsistent versions of the first round, then that could potentially be a security breach. So the way that this is handled is that you do not want to just sort of give away the round 2 of the honest parties based on the version that they got, and instead you want to use something like a conditional disclosure of secret or gabble circuits, whatever you like to think of it like. So basically you want to use something like that that will hide the round 2, and it will only conditionally release the round 2 computed based on a bit B if a condition is true. And here the specific condition is that if the token for B is reconstructed, only then the value for round 2 computed on B will be revealed. Otherwise, it will not be revealed. Similarly, the second party is also going to sort of give its second round message hidden and compute it based on B, which it will reveal only if the secret token, say, for B is reconstructed. Now, if you follow this approach, and somehow if we guarantee that exactly one secret token for one value of B will be revealed. So if I guarantee to you that you will either only reconstruct the secret token for B being 0 or for B being 1, then we are happy. Because in that case, we will be sure that all the round 2s are all computed for the same version of the B, and then we are consistent. So this is what it boils down to, that now what you want is basically a way to make sure that exactly one secret token for a unique value of B is reconstructed. So for this, we introduce a new building block, which is a tool that we call one or nothing secret sharing, which probably could have other applications. So here what this tool enables is it allows the dealer, and who is the sender in this case, to share a vector of secrets. But here we only have 2 secrets, which is one for the token corresponding to B equal to 0, and the other for the token corresponding to B equal to 1. So the dealer simply shares a vector of secrets. And we also allow parties to vote for which of those secrets they want to see reconstructed. Okay? So in our context, the vote will basically be the version that they got. So because party 1, she got 0, she's going to vote for 0. Party 2 got 1, so he's going to vote for 1. And we also allow some parties to abstain from voting. So if they got nothing, say that they vote for bot. And why we allow for these bot votes is because we want some guarantees even when the sender is honest. That's why we are having this provision of bot votes. So now the guarantee is that the dealers shared multiple secrets. The participants got to vote for which secret they want to see reconstructed. And the guarantee is that at the end, at most one of those secrets is going to be reconstructed. So now if we have this, then we can plug it in and get something that is secure. And in fact, since we want to maintain round optimality, we also want this property that the sharing, voting, and reconstruct, we sort of want everything to happen simultaneously over a single round of broadcast, because we want everything to happen in the second round in this context. So we want a scheme in a way that the sharing and voting and the conditional reconstruction all can happen in a non-interactive way. So this is the building block that we need, and we have a very simple construction for it. So I'll explain you the version with the correlated randomness, because that also has the main ideas. So let's just assume that as a part of the correlated randomness, each of these parties has 3 keys, one for each possible choice of their vote. So the first party has a key for 0, a key for 1, and a key for bot, and so on. But these keys are different. So the key for 0 for party 1 is different from the key for 0 for party 2. So you have 9 different keys here. And say that the dealer has access to all of them. Now, the voting algorithm is very simple. What a party needs to do to vote for a particular choice is that they simply have to give away the key corresponding to that choice. So if the first party wants to vote for 0, she simply has to give away her yellow key corresponding to 0. Similarly, the second one just has to give away his blue key corresponding to 1, and so on. So that's how the voting looks like, that just give away one of your keys based on your choice. Now, how does the sharing work? So the sharing is basically that the dealer, what he's going to do, he's first going to additively share each secret. So in this case, this token b equal to 0 is additively shared. And now this is going to be communicated by using this ciphertext. So this ciphertext is nothing but PI's additive share, which is encrypted using the 0th key of PI. Okay, so this is the additive share of 0 that PI has, and you're simply encrypting it using PI's 0th key. Now, similarly, you will have additive shares of the other secret 1 also, but in this case, they are going to be encrypted using the blue key corresponding to 1 of the party PI. And now the secret sharing scheme is actually 2 levels for us. So first level is that you have this layer of additive sharing. And then now the second level is that each of those additive shares are now going to be threshold shared using something like a Shamir secret sharing, say with threshold T. So now these are going to be useful when some parties are voting for bot. So now what happens is that to communicate these threshold shares, we will be having double encryptions of some sense. So this basically what it corresponds to is this is the additive share of PI corresponding to 0, but it's the threshold share that PJ has. So this is the threshold share that PJ has corresponding to PI's additive share, and this will be encrypted using PI's pink key for bot and PJ's yellow key for 0. So this is going to be basically something that you want to reveal in case PI is voting for bot and PJ is voting for 0, then you want this share to be revealed. But you'll see how this is useful in a moment. So similarly, you will also threshold share the additive shares for 1, and again, they are going to be double encrypted, this time using pink keys of bot for PI and blue keys for 1 for PJ. So now let's just analyze the properties of this scheme. So the first claim is that if some of the parties vote for 0 and some of the parties vote for 1, then the claim is that none of the secret tokens are going to be reconstructed. So why is this true? Let's take this case itself where somebody has voted for 0 and the other person has voted for 1. So we are sure that the secret token for 0 is not going to be reconstructed. Why are we sure? Because we will be missing P2's additive share of 0. Okay? Because P2 has voted for 1, so we only have the blue key corresponding to P2. So the first level of ciphertexts are useless for us because we are missing P2's yellow key for 0. And also the second level of ciphertexts are also not useful because we are also missing the pink key corresponding to bot of P2. Okay? So overall, we are missing P2's additive share of 0, and that's how, yeah.
Doesn't the P2 knows their yellow key, so P2 can compute the 0?
Yeah, so in this case, for this particular case, so it depends. So because you're asking if P2 can reconstruct the label for 0.
Yeah, the other parties don't know P2's yellow key, but P2 knows his yellow key.
Yeah, he should be able to do it, but now then you have to also consider what is happening with respect to P3's keys and so on. But for this example, it's true that P2 locally can. Yeah.
But you don't care about secrecy, right? This should be like a broadcast value, so we just care about consistency, not about the secrecy of the value, right? The
yes.
original protocol, you just want to communicate it to everyone.
So we want that exactly, so in the context of we want that exactly one of those labels should be reconstructed, so we want to make sure that both are not. So it would be a problem if P2 gets the labels for both 0 and 1. It would be a problem.
Why? Because it makes it inconsistent?
Because then we have these next message garbling. So now if he can compute the round 2 of an honest person based on both the values of B, then it's going to be a problem. Yeah. So we do need this property that also P2 locally should not be able to get the labels for both 0 and 1. But just for the sake of this example, so that it will be true because of what's happening with P3 and so on. But then in this example, yeah, at least the others will be missing P2's additive share, let's say. But we're also sure that also the 0 is not going, also 1 is not going to be reconstructed because we will be missing the additive share of P1 corresponding to 1, right? So even if P2 gets 0, he will not be able to get 1 for sure because he's missing P1's additive share, okay? Yeah. But then now the point is that if there are no contradictory votes, but the parties are somewhat aligned, that say that a lot of them are voting for n minus t, and I'm assuming an honest majority here, say that n minus t are voting all for B, and then the others are voting for bot. Now in this case, the claim is that the token for B will be reconstructed. So why is this true? Because for the ones who voted for B directly, we can just use their first level of ciphertexts, and we can directly get their additive shares. And for the ones who voted for bot, we are missing their additive shares, but this is where the second set of ciphertexts are going to be useful. Because the ones who voted for bot, say PI voted for bot, then we can use PI's pink key, and we can use the Bth key of the people who voted for B. So say PJ is somebody who voted for B, and PI is somebody who voted for bot, then we can sort of decrypt this and get the threshold share of PI's additive share. And if we have enough threshold shares, we can reconstruct it, get the missing additive share, and get the label. Okay? So this is the property that if sufficiently many of them are sort of aligned in the same direction. Yeah, sorry, there's a question.
These two properties, don't they contradict one another?
Sorry?
What if there's no one voting for bot?
So are they all voting for 0?
N minus t vote for B,
Yeah.
and no one votes for bot, then you should have nothing reconstructed, right, from the first property.
If n minus t vote for B and nobody voted for bot, but so what are the others doing? They have to vote for something.
I think the others vote means everybody else.
So in the context of our protocol, everyone has to make a vote.
Everybody else, I think.
1 minus B. What if they vote for the other bit?
B bar.
So if they vote for B bar, then nothing will be reconstructed.
Whenever there are different votes, nothing is constructed.
Oh, I see.
If it's just B and
If
bot,
it's just
then
one
there's
vote and
enough
bottom,
Bs.
the second one, I see.
Yeah, if it's just one vote and bottoms, then it's the second one. But if it's even the moment you have anything contradictory, nothing will be reconstructed. Yeah. Okay. And but now if you notice that now we have this property because sharing is nothing but broadcasting these set of ciphertexts, and that can happen simultaneously to the voting because voting is just giving away your key. So that can happen at the same time as the sharing is happening. So this is a property that is helpful for us to maintain the round optimality. Okay. So are there any other questions about this slide? I can leave it for a second. Yeah.
So if you have correlated randomness, you can also do information-theoretic signing, right? And once you have information-theoretic signatures, like why use encryption instead of just information-theoretic signatures?
So, I mean, I've hidden sort of many things under the rug because we want the property of identifiability also. So we do want that if, for example, because people can always say that they got nothing, even if you have signatures. But always it's still possible to have the attack that somebody says that they got nothing. Okay? So we want to still be robust in that situation. That's how the bot votes are helping us because that is still helping us to be robust when the sender is actually honest. Yeah. But we are using signatures also for like making sure that we don't have contradictory things, and if we have contradictory things, we can catch the cheater and so on.
But you still assume here correlated randomness, right?
Yes.
So you can also assume information-theoretic YAO and do even more magic, right, with information-theoretic YAO.
I mean, possibly. Like, I don't know if it will all squeeze into 2 rounds, but yeah, I'm not sure. Okay. So this was one of the building blocks that we introduced, and then we also had a variant of it without the correlated randomness setup, where we, but then there it's like we have some different thresholds for it. So there we move to super honest majority instead. Yeah. Okay. So now next I want to give you a sort of a glimpse into the lower bound. So our lower bound is for the information theoretic setting, specifically statistical MPC. And for statistical MPC with honest majority, 4 rounds are known to be optimal. And what this result is saying is that if you were missing broadcast just in the 2nd round, even if you had broadcast in the 1st, 3rd, and 4th round, we are saying that still you cannot get statistical MPC with guaranteed output delivery. Okay? And I want to just clarify some notation that when I say BC, I actually mean that you have both broadcast and point-to-point channel. But for the last 2 rounds, you can sort of assume without loss of generality that it's only having broadcast communication. That's because even if you had some private communication in the last rounds, you can always emulate it by exchanging some one-time pads privately in the earlier rounds and then broadcasting the masked communication. So this is without loss of generality to simplify the proof that the later rounds are using just broadcast. Okay? So now the proof is by contradiction. So assume that somehow you managed to design a protocol and you did not use broadcast in the 2nd round. Then I'm going to show you the proof for 3 parties with 1 corruption. So now consider this situation scenario where these 2 parties are honest, so everything is good between them. But what the corrupt P1 is doing is that he is honest towards P3, but he is dropping his point-to-point message towards P2. And he's also ignoring whatever P2 is sending to him, okay? And now instead, what this corrupt P1 will do is that in his head, he's creating this experiment in which he is like creating a version of a fake P2 and a fake P3. So he's sampling randomness on their behalf and then just computing what they would have sent to each other over the point-to-point channel using that randomness, and specifically what this fake P2 would have sent to P1. All this is something that P1 is just doing in his head. So this is similar to the hexagon argument for those of you who are familiar with the classic broadcast impossibility. So, but then when he's sampling the randomness and doing this experiment in his head, he's doing it in a slightly clever way, in the sense that the randomness should be sampled so that it's consistent with their 1st round broadcasts. So here is where we will be using the unbounded power of the adversary, that you're sampling randomness such that it's consistent with their 1st round of broadcast. Now what P1 is going to do, he's going to basically act as if he has been talking to this fake P2 all this time over the point-to-point channel. That's what is going to be P1's strategy, that over the point-to-point channel, and when he's acting towards P3, he's just going to be acting as if all this time he has been talking to this fake P2. And the point here is that until this real P2 has to wait until the next broadcast round in order to be able to make a public complaint. So until this real P2 is able to make a public complaint, until then P1 has some sort of plausible deniability, because he can always pretend that he has been talking to this fake P2 all this time. Now, as far as P3 is concerned, this looks similar to another situation, which is scenario 2, where P2 is the corrupt one. And in this situation, what P2 is doing is he's acting honestly towards P3, but then he's just making a false complaint about P1. Even though he received messages from P1, P2 is going to pretend that he did not. And what he's going to do is this time, P2 is the one who is doing this experiment in his head. So he's creating these fake versions of P2 and P3, sampling randomness on their behalf. And now he's going to send point-to-point messages towards P1 as per this fake P2. Okay? So as far as P3 is concerned, he doesn't know if he's in this world or in this world, because in both these worlds, the views of the parties are identically distributed. But in this one, P1 is corrupt, but in that one, P2 is the corrupt one. So now, since we're assuming that this protocol achieves guaranteed output delivery, then we can basically, suppose this was the function being computed, for example. It's just a function like an OT where P1 is the receiver and P3 is the sender. So say that this was the 3-party function being computed, and we're assuming it's with guaranteed output delivery. So this means that the honest P1 in this situation should get the correct output XB, because it depends on the inputs of honest P1 and P3. Okay? So now if this is true, and in scenario 2, P1 gets this output XB, it means that also the corrupt P1 here should be able to obtain the output XB because his view is identically distributed to the honest P1's view there. Specifically, this corrupt P1 should be able to get the output XB even if he does not talk in the last round and he's rushing and silent in the last round. He will still be receiving all the incoming communication. So now the main observation is that if we are trying to prove security of this protocol and we want to design a simulator against such a corrupt P1, we will have to successfully extract B at the end of the third round itself, because in the fourth round, the P1 is obtaining the output. So now we are going to be assuming only straight line simulation, and we are also in the plane model. So what this means is that what does the simulator have to work with? He only has the broadcast messages of P1, and he has the point-to-point messages towards P3. So though the simulator was acting on behalf of P2, he sort of got no advantage from it, because in this attack, P1 did not send any messages to P2. Okay? So basically, the main observation is that the simulator does not really have any advantage by acting on behalf of P2. And whatever the simulator is seeing is something that a real P3 in the protocol can also see. So that's the main intuition here, that by doing this attack, the power of the simulator sort of got reduced to something that a real P3 can also do. So now we basically, what we do is just to sort of wrap things up, we come up with another scenario, the final one, where P3 is the corrupt party. And now, if you observe here, the roles of the P2 have switched. So now, in this case, the fake P2 so far is the real P2 here. And then the whole point is that P3 is just going to be creating sort of the same situation as scenario 1, so that he's able to run the simulator from scenario 1. Okay? So the main takeaway from here, even if you sort of lost me, the main takeaway is that in this scenario and the first attack, the P1 somehow completely disentangled himself from the true randomness of P2 by doing this attack. So because he disentangled himself, the simulator lost that power, and that's why the real P3 is also able to sort of do the same attack that and run the simulator algorithm. Okay? And this would be a final contradiction, because if P3 here is able to run the simulator and extract B, that would be a contradiction, because that would violate the privacy of P1. Okay? So this is sort of one of the lower bounds that we have. And interestingly, this holds even if you had several rounds of point-to-point communication in between, not just one round. If you had several rounds also, this argument would go through. Because like I was mentioning before, until the real P2 gets a chance to make a public complaint about broadcast, until then P1 can do this attack of having this deniability of what he's receiving over the point-to-point channel. Okay? So with this, I sort of want to conclude the talk. So here, what I explained to you in the end is our most latest work, which is we explored statistical MPC with guaranteed output delivery, but maybe with weaker guarantees like abort or identifiable abort, maybe the optimal use of broadcast would turn out different. And something else that has not been explored is about what happens for perfect security and the computational case, both in the plane model. And lastly, I've only been talking about reducing the number of rounds that use broadcast, but it's also interesting to understand what you're broadcasting and the size of the messages that you're broadcasting. So that will also be nice to optimize. So that's it. Thank you for listening.
A quick question.
Yeah.
On one of your first slides, you had some question like, you have a protocol with 4 rounds, 2 of which are broadcast, but you have a protocol with 7 rounds, only 1 of which is broadcast.
Yeah.
Does your work shed light onto those kind of questions?
So, I mean, I think we're mostly leaning towards the 7-round thing being more round efficient. But of course, it depends on how the distributed computing committee also progresses in terms of the expected round complexity, like how much those constants have been reducing over the years. But it's still of the order 10 or something as of now, I think, as far as I know. So, yeah, I mean, we can't give a definite answer because we have to keep up with the progress in that side. Okay.
I'll go ahead.
Yes.
I was going to ask Ron first, but I'll just embarrass myself. Can you go back to the slide where you have the table?
Yes. This one?
Yeah,
or-
so
yeah.
my question is about the identifiable abort, the requirement that broadcast is required in every round.
Yes.
And I guess I was going to ask Ron, in our paper for multiplier, I don't think we have broadcast in every round, right?
But is it round optimal?
Okay, so that might be the gap, okay.
Because for round optimal protocols, we are saying it should be over every round. But I think in general, if you allow for like more than round
Well,
optimal,
I was going to say, this is basically, your argument is very specific. So there might exist protocols for which you have to have it, but could there be some MPCs with like bizarre type of, like,
Yeah, definitely. Because once you have a protocol with 2 rounds, you can have protocols with any number of rounds that are over point to point, but you are used to broadcast.
oh, I see, okay.
That's mostly first and last round. The 2 comes for first and last, but this is 2 rounds, so
Okay.
you need both.
Okay.
but I mean also for the
For 4-round also.
4-round in the plain model, also we are saying that
Yeah.
all 4 should be over broadcast.
So if you have more,
But if you have many rounds, then I think you can get, even with 1 round of broadcast, I think you can get identifiable or bot. Because there is some compiler, I think by Jonathan Katz or something long ago, that they show how to sort of compile any constant round protocol that is using several broadcasts into something that is using only 1 broadcast. But then that will be with some inflating the round complexity. So it will not maintain the round optimality.
You can think of running broadcast in between, right, over point to point. If you allow yourself to expand.
Yeah.
Right, if there are no further questions, let's thank the speaker again.